I'm just looking at what we did the last time.
Okay.
So it really doesn't matter.
Question. The base.
So you want transformations on the cube root.
The cube root with the stretching and
The stretching and shrinking is
Okay.
the tough one.
Okay, the horizontal stretching and shrinking or the vertical stretching? Because they basically mean the same thing, but it depends. So if you have, let's say, the cube root of x, this is the base function. So you can determine, Alex, you wanted to say something?
Oh yes, the base functions. You know how you drew them out with specific lines. Are those always the same lines for every base function, or does it vary?
Every base function is different. We have 7 different ones.
So like for linear, it was like a straight. If I'm not mistaken,
Yes,
a straight
yes.
line. Is it always a straight line for every linear equation we do?
The base function
Yeah, if the base function.
with no transformations. There is only one, y equals x. But if you say y equals x plus 1, it's a totally different story. You have a shift of left 1.
Oh yeah, I understand.
So, but it's the same function. So it depends on which function you start with. Yeah. So if you want this will be the cube root of 1/2 x. Is that what you meant, Tim?
Yes.
And if you want, for example, this, then this will be the cube root of 3x.
Either one or both.
Okay, so let's do this. Okay, in y equals, I will have 3 functions. I will have x raised to power 1/3, because that's what the cube root is, correct?
Yes.
Okay. Then the next one I will have in parentheses 0.5, which is 1/2, right?
Yes.
1/2 x. And again, the power is 1 divided by 3. And the last one, we decided to have 3x. Close. And the power, of course, is 1/3. Okay? So let's graph all of them. Okay, here comes the first function, which is the base function, the blue. Now, it would be slightly difficult to see what's happening here, but let's, okay, so here is the red function, which is 1/2. But as I said, unless you see that it's a horizontal stretching, it's, in other words, a vertical shrinking of the graph. So this was the second one, and this was the third one, right? So the third one was 3 times x, right? That's what I put in.
Yes.
So that's a 3 times x. And that is a horizontal shrinking of the graph. That's why it opens up. A horizontal stretching is leaner. Horizontal shrinking stretches up. That's why the third one is further away from the x-axis than the other two.
You say that one more time.
So when we change x into 3x, we're doing this, which makes it wider.
Right.
When we change x into 1/2 x, we're doing this, which makes it flatter, thinner. It's exactly the opposite of what you expect. Good. Perfect question. Anything else? Yes, please. Honey?
So basically, when you say like horizontal stretching or shrinking is like the same thing.
No. Horizontal stretching is this.
Yeah.
Horizontal shrinking is this. Yeah. When I stretch, I become leaner, right? When I shrink, it becomes wider. But it's under the same category. But they're not the same transformation.
So this is horizontal.
Both. The red one is horizontal stretching. The last one is horizontal shrinking.
Okay, so they go horizontal then not vertical.
Horizontal both. However, it's a very good question. Every time I shrink horizontally, I stretch vertically. When I stretch horizontally, right, I shrink vertically. When I stretch horizontally, when I shrink horizontally, I stretch vertically. That's exactly how I illustrated it. By starting with the x cubed and then changing x into twice x or changing x into 1/2 x to show what really happens. Yeah, because it's kind of difficult to, at least the first time we see it. Yes, next question. Perfect question, Tim, thank you. Anything else? Have we tried anything else? Anything else? Anything else from my math lab? Anything else from the previous lecture? Anything? Anything? Alex, go ahead.
Absolute 1 negative x over 4.
I'm not sure what you're saying.
Oh,
Can I see?
this one over here.
Okay, so you're trying to, did you look at the solutions?
No, I've just been going through it.
Yeah, okay, so that's fine. So we have 1 minus x divided by 4 in absolute value minus 5 less than or equal to 1. So we want to go back to our test. So first of all, we have to add 5 to both sides. So this is 1 minus x over 4 less than or equal to 6. And since this is less than or equal to, we have this. Anything else you try at this point cannot be accepted. Because if you remember, we said the absolute value is not the grouping symbol. You cannot distribute. You cannot take anything out. This is carved in stone. I do not know how to solve this unless I know how to translate it into that. Is that clear?
Kind of. So can you iterate more so you cannot solve that if you don't know how to turn it into that?
You don't know how to solve this?
Yeah.
You have to change it into this.
Alright.
Remember we said try to find numbers whose distance from 0 is 6 or less. 6 or less. 6 or less. From negative 6 to 6.
Alright, so do
So first, then I have to subtract 1. So this is negative 7 less than or equal to negative x over 4 less than or equal to, I subtract 1, 5. And then I multiply all sides by negative 4. So this is 28, this is negative 20, and this is x. So obviously I have to switch the inequality symbol. If you have your cell phones on on the table, I will ask you kindly to remove them. Please. So in interval notation, negative 20 to 28, because you have to read it from the small to large. Any questions on this? Anything else? Anything else? Okay, so we are continuing now with algebra functions and transformations. That is section 2.6. Algebra of functions and function composition. So algebra of functions means we are now adding functions to create new functions. We are given two functions. We are asked to create new functions. Okay, so let's see how that is possible. There are 5 different possible ways, but 4 in algebra. I can add, subtract, multiply, or divide functions. That's what algebra of functions means. It means adding, subtracting, multiplying, or dividing functions. So obviously, the notation is, in my opinion, self-explanatory. I'll ask you in a minute, what do you think these will equal to? So the first one, what do you think it equals to? And I will write it down by definition. It can only be f of x plus g of x. The next one, of course, it can only be f of x minus g of x. The next one is f of x times g of x. Of course, f of x over g of x. But this one, the last one, has an if. What does that mean? It has an if. What does if mean or refer to? Please. Yes, Jordan?
Is 2.8 or 2.6?
Oh, I'm so sorry. You're right. I meant 2.6. Thank you very much. Sorry, my apologies. Yeah, we just finished 2.5, and I was supposed to continue with 2.6, of course, but for some reason I wrote 2.8. Thank you. So if what?
If g is 0.
If g is not 0. If g is in 0, we are in big trouble. Very good. Any questions? Okay. So
Why can't you?
can anyone explain why the denominator of a fraction cannot be 0? Yes, please, Celia.
Because you can't divide by 0.
Thank you. Division by 0 is undefined. Thank you very much. Okay, so let's take a look at two graphs. I'm going to make up two functions. Here's one. And I'm going to say it's between -10 and 3. And this is f of x. And here's another one. Let's say between 0 and 10. And that's g of x. And I'm going to ask you to determine f minus g of -2. Without looking at the graph, what will you say this equals to?
F of -2 minus g.
Oh, very good. F of -2 minus g of -2. So f of -2 is this height. I don't know, let's say it's 7. But what about g of -2? G is not defined at -2. The domain of G is between 0 and 10. The domain of F is between -10 and 3. So this function cannot be created for this value. So then for which values I can ask you to create any of these four functions? For which values of x? Of course. What do you think that is called? If they don't have it, we cannot create functions that are additions, subtraction, multiplication, and division of different functions. What do you think they need? And if they don't have it, nobody cares about those functions. Of course. If they do not have a common domain, we cannot create those functions. Okay. What is the common domain for f and g from my graph? CD, the common domain. What is it? Indeed, between 0 and 3. So if I want to ask you, create f over g at 1, you will be able to. If I ask you find fg at 2, you will be able to. But if I ask find fg of 4, you will say, sorry, it does not exist. Because the common domain is between 0 and 3. So in order to add, subtract, multiply, and divide functions, I have to check for the common domain. If there is no common domain, functions don't exist. So let's look at the following problem on 28 on page 310. We are given a function obviously this is a ratio of two functions. I hope you agree. So this is a function at the top and this is a function in the denominator. This is like, let's say, f divided by h, two different functions. We're asked to find the domain of function g. That's the question here. So let's take a look at this function and identify restrictions. What do I need to write before I even attempt to find the domain of this function? What do you think we have to write? Excellent. That's our first condition. X minus 6 cannot be 0, and of course x cannot be 6. Excellent. That's our first condition. Now remember, we know a lot about this function. We know its domain. We know how it looks like. We know exactly where it's going. We know the base function of x, the square root of x, and I know where the square root of x minus 3 is going. Where is it going? To the right 3. So then, obviously, x minus 3 has to be, if it's going to the right 3, it's under the square root. We know that from a long time ago. What do I have to write about x minus 3? Say it again. No, there is no such thing under the square root. When we graph the function f of x equals the square root of x, we wrote that this quantity has to be greater than or equal to 0. I have to do the same thing for this function. We already know what the domain is. It shifts to the right 3. So what do I have to write?
Greater than or equal to 0.
Excellent. Greater than or equal to 0. Awesome. So then x greater than or equal to 3, which we already knew. But now I have to intersect these two solutions. Because I'm looking for the common what? Correct. So this can be considered f over g, or it can be considered f times g. I'm sorry, f times h, where h is 1 over x minus 6. So we see there are two conditions. Oh, okay, greater than or equal to 3 is this. And it says not 6. Not 6. Can anyone give us then the domain of function g? Can anyone give it a shot? Anyone? I mean, it's right here. You just have to read it. Yes, with a bracket, 3, comma.
6,
Very good. 6, union.
parentheses 6.
6 to infinity. Very good. In plain English, everything from 3 to infinity except 6. Very good. Okay, so let's look at one other. Let's say problem 8, which is g of x, 2 divided by x squared plus x minus 12. We're asked to find the domain of this function. What do I have to write? In order to find the domain of this function, I have to write what? Can anyone dictate?
X squared.
Yes. Plus x. Then? What else? Yes. Awesome. Yes.
Can't equal 0.
Of course. We know that from our experience already. So this is x plus 4 and x minus 3. So there are two possibilities. Cannot be negative 4 and x cannot be. Very good. So now we can write the domain. Can anyone tell us the domain? Give us the domain so we can write it.
Bracket 4.
How can I put a bracket since it cannot be negative 4? I cannot put a bracket. A bracket means the negative 4 is included. Yes? Very good. Negative infinity to negative 4, union negative 4 to positive 3, union 3 to infinity. In plain English, everything but negative 4 and 3. Great job. Okay, so now let's say we are given two functions. For example, 36 on page 310, and f of x equals 6x squared minus x minus 1, and g of x equals x minus 1. We're asked to find four functions, the sum, difference, product, and ratio, and their domain. Can anyone give us the domain of f, and can anyone give us the domain of g? What kind of functions are these?
Linear.
Not both.
Quadratic.
Quadratic and linear. Very good. Now we imagine their graphs. We know how a quadratic function looks like. We know how a linear function looks like. And just tell me the domain. Yes, please.
Can I try the bottom one?
Yes, they are the same. They are polynomial functions. They're all the same.
So this is
So negative infinity to infinity, they're all polynomial functions. Polynomial functions don't have restrictions. They're not like rational or radical. So when we look at polynomial functions, we know, oh, they're friendly, no restrictions. Now, can anyone give us the common domain? Right. The common domain must be negative infinity to infinity. Now, also, this, which is the common domain, is always the domain of the sum, the difference, and the product. Always. You don't have to write it again. So once you establish the common domain, you do not have to write again the domain of the sum, difference, and product. Notice that I did not say anything about ratio. I only said sum, difference, and product. Okay, so let's find them. So f plus g, by definition, I have to write a definition, is f of x plus g of x. And now I have to replace them. I will replace 6x squared minus x minus 1 plus x minus 1. I have to combine like terms, and I get 6x squared. These two go away, minus 2. So this is a new function that was determined by adding the given functions. It's a totally new function, and we know it was built by adding those two. In the same way, we will determine the difference. You have to write the definition at all times, so we know, don't make a mistake. So this is 6x squared minus x minus 1 minus, in parentheses, x minus 1 before you distribute. Stop me if you have any questions. In this section, there is a lot of writing, but I don't think it's anything. Yes, please. Alex, go ahead.
Why are we solving for all the
We're not solving. We're just determining new functions. This is not an equation. We're not solving for anything. We're not evaluating. We're only using, I saw that 1 second. So we are only using two functions to create new functions.
Alright, so I know we got the common denominator, so why are we
It's not the common denominator, it's the common domain.
just common thing?
Correct.
So why are we using that to look for different equations?
The problem is asking us to determine all four functions and their domains. So I had to determine the common domain, the domain of each function, the common domain, because that's always the domain of the sum, difference, and product. I don't have to write that again. But when I determine the ratio, that's a different story. It could be the common domain or not. There is no guarantee. That's why I did not list the ratio here. Was that the answer, the question? Okay. Yes, please.
So would you distribute the negative?
Yes. Yes. So 6x squared minus x minus 1 minus x and plus 1. These two now go away, and we have 6x squared minus 2x. So this is a totally new function, totally different. It was determined by subtracting the original functions. Any questions? Are we okay with this so far? Okay, so let's look at the product, which is 6x squared. Oh, I don't want to do that. I want to write the functions first, the definition of this. So then I copy 6x squared minus x minus 1 and then x minus 1. So I multiply a trinomial by a binomial. So I have to distribute and then negative 1. So x times 6x squared, 6x, very good. X times negative x, perfect. X times negative 1, negative 1 times 6x squared, very good. And then plus x and plus 1. Of course, I will try to simplify as much as possible. We're not solving, we're just combining like terms. So negative 7x squared and plus 1. This is a totally new function, and it was determined by multiplying the given functions. Finally, f of x, f over g of x is by definition f of x over g of x, which is 6x squared minus x minus 1 over x minus 1. There is nothing we need to do here. However, we have to find the domain of this function. From the common domain, which happen to be all real numbers, I must subtract, remove, I should say better, I must remove those values of x that make the denominator 0. So x cannot be 1. Very good. So now what is the domain of the ratio then? Very good. As you see, the domain of the ratio did not come up to be the same thing. There is a fourth way of, there is a fifth way of determining new functions, and that is totally different. It's called function composition. And the two notations are, main notations are f comp g, and the other one g comp f. Of course, I can create a composition with f, so f comp f. I can have f comes g, any different combinations that you can think of. So by definition, this means f of g of x. Can anyone give us what the other function means? Right. Very good. But what is behind this? What procedure is this? Because it's not the sum, it's not the difference, it's not the product, it's not the ratio. It's something totally different. Okay. Let's look at three bubbles. Now, in f comp g, which of these functions is the inner function? The function that is applied to x first. Is it g or is it f? Of course, it's the inner function. So then you're saying to x, you are applying g to get a number g of x. And then you apply to this number what function? Excellent. Well done. So this is f of g of x. So, and of course, this will be, first will be x, and then f of x, and then g of f of x. Now, here's the question. Do these two functions do they need to have a common domain? The answer is absolutely not. We don't care whether they do. We don't care whether they don't. Here, the situation can be way more complicated. Here it is. Can you please tell me what, for this function g, what does this set represent? The domain, correct? It's where the x values come from. So this is the domain of function g. Would you agree? Now, what does this set represent for function g? This is for the values of y. How do we call it? If this is exactly. So this is the domain of g, and this is the range of g. Now forget about the first function and tell me, oh, I'm sorry, this is f, sorry. Now please tell me, what is this function for f? I'm sorry, what is this set for f? Domain. So this is also the domain of f. So this set is at the same time the range of g and the domain of f. So what could go wrong here? A lot. And what could go wrong is, yes, go ahead, Alex. No, what can go wrong here is that g brings a value here that f cannot be applied to. So for example, if f is 1 over x, and let's say g of 1 is 0, we're in trouble because f cannot be applied to 0. So this is a topic that I will not ask you for. I don't know if you're going to have, if you encounter something like this in my math lab, please bring that problem to class so we can solve it together. But this is a more complicated situation. They may choose problems that work. That's possible, but I don't know. I have to look at the problems. So the situation here is the range of g may not work well with the domain of f. That is the potential problem. No common domain is required here. The range of g and the domain of f may not work well together. See, if these two have gaps or problems, then the function needs domain adjusted. Okay? I'm not going to ask you to find the domain of function composition. So by the way, this is called function composition, and this is read f comp g is f comp g, the composite of f and g, or simply f comp g. It's up to you. The composite of f and g, or in short, f comp g. Of course, g comp f. So let's take two functions, like for example 74 on page 311, and let's create the function composition. They want us to determine f comp g. They want the domain of f comp g. I think it's beyond the scope of this course. If you want me to show how it's determined, I can. So for now, let's just determine f comp g, and we can also determine g comp f. Okay, so like before, we start with the definition. Please always write the definition so you don't make a mistake. F comp g represents f of g of x. And now, instead of g of x, don't cross it out like that, I'm just making a point. I have to put the square root of 2x, 2 minus x. So this is f of the square root of 2 minus x. And now I look at f. What does f say? F says blah squared plus 1. But this is my blah now. That's my blah. So please dictate what I should write. And if it's correct, I will write it.
X squared plus X.
Careful. So f says f of blah equals blah squared plus 1. This is the blah now. So what do I write? Give it a shot. We've done this before, evaluating functions. It was a long time ago. Very good. The square root of 2 minus x, everything squared plus 1, of course, which is 2 minus x plus 1 or negative x plus 3. We've done this a long time ago with the difference quotient. We know how to evaluate a function for anything we can think of. Now we want to do the other one, g comp f of x. So this is g of f of x, which is g of, and I look at x, and this is x, f of x, which is x squared plus 1. But now I look at g. G says g of whatever is the square root of 2 minus whatever. Can anyone dictate? Yes, of course, the square root, yes.
X squared.
We're here with the square root. I have to write 2 minus, in parentheses, excellent, very good. So this is 2 minus x squared and minus 1, or the square root of 1 minus x squared. Any questions for me, please? Yes, please, go ahead.
Can we do another one because that was
Yes.
like confusing.
Oh, which part was confusing? And yes, we will do another one, of course.
The part where we have to, like, I get the part where we put the g of x in for g of x, but like it's the other part.
The f of x, yeah. Like why did you put it in parentheses?
Which one?
Like the square part.
Okay, so when we look at function f, I would like to explain this one and then find another, just to make sure that this is clear for everyone. So I look at this function, and a month ago, we decided that when we look at a function, we are able to identify the pattern. The pattern says f of whatever you want equals whatever squared plus 1. That's the pattern, and this is what I have to use. Whatever squared plus 1. We agree? So if I have here 1500, then I have here 1500 squared plus 1. If I have here x plus h, then I have here x plus h squared plus 1. If I have here the square root of x minus 2, or 2 minus x, I have here the square root of blah, blah, blah plus 1, correct?
Yeah.
Okay, so then when I look at the function, and I have to plug in the square root of 2 minus x, and that's exactly what it tells me. It tells me blah squared plus 1. This is my blah, and this is in here now, so blah squared plus 1.
Okay, so basically you just substituted
That's what the function represents.
one function and for x
Inside of the other, correct. So then this one squared will be 2 minus x plus 1, and then we get negative x plus 3. If you say that this is okay, then we'll continue, and then we'll choose another. Is this okay, everyone? Alex?
Yes, yes.
Okay, perfect. Now we want the other one. Look at what G says. G says of whatever is the square root of 2 minus whatever. If I have here 1500, then I have here 1500. If I have here x squared plus 1, I have here x squared plus 1, correct? Good, so that's exactly what we have. So instead of this function, which is x squared plus 1, I have to have the square root of 2 minus. If I don't put parentheses, I will omit to distribute the negative 1 to both. I have to put parentheses because this is minus. So then I copy 2, I copy negative x squared and minus 1. So this is, after I combine like terms, I get 1 minus x squared. Is this okay? Everyone?
Yeah.
Better? Now you understand the parentheses? Okay.
I'd still like to try another one.
Of course, but is it clear now? Okay, because I don't want to leave anything behind. Okay, so in another example, let's say we have 72, same page, 311. So we have f of x equals the square root of x, and we have g of x equals this, oops, I'm sorry, x minus 3. Do not write the square root.
What is it, just x minus 3?
Do not write the square root. So we are asked to determine both functions, f comma g and g comma f. So f comma g, always write the definition first. So it's f of g of x, which is f of x minus 3. And now, what would you write? Say it louder.
Square root of x minus 3.
That's it. Indeed, perfect. Well done. We also want to determine g comma f. Are you with me, everyone? G comma f. So this is g of f of x, which is g of the square root of x. And now please tell me what to write for g. The square root of x minus 3 outside. Excellent. Well done.
Oh, okay.
So now we want to find, we want to talk about function decomposition. Function decomposition. So let me look at an example, and then you will give me the answer for another one. So let's say 78 on page 311. We have h of x equals the square root of 5x squared plus 3. So we're asked here to find two functions that this one will represent or be the same when we create the function composition. So we want this, and we know that this function is the inner or the outer. So this is f of g of x. Maybe this is easier to see. What is g? Is g the inner or the outer? Perfect. Indeed. Excellent. And then f of x will be? Very good. So then, thank you. So then we will look at decomposing this function. So let's take a look at this, and please tell me which will be, if you were to evaluate this function for x equals 0, which portion will you evaluate first? And that will be our g of x. And there is more than one correct answer here.
X plus 3.
Say it again.
X plus 3.
No, because it's not x plus 3. It's 5x squared plus 3, which is a totally different story, right? So then will be 5x squared plus 3 will be the inner function. And when we get an answer, one number, which function I apply to this number? Which function I apply to this number as the outer function? That's it. So f of x equals the square of x, indeed. If you compose these two functions, it's guaranteed that you will determine function h. So let's look at 80. On 311, the same question. We have h of x, we have the absolute value of 3x minus 4, and they want us to find or decompose the function into an inner and an outer. Inner, outer. What would you say?
3x minus 4 will be the inner.
Indeed, excellent.
Absolute
3x minus 4 will be the inner, and the absolute value of x will be the outer. Excellent. Well done.
So you still have, you said, a couple of different answers.
Yes, yes, because someone may say that one function is 3x, and the other function is the absolute value of x minus 4.
Okay.
Yeah, there's more than one correct answer here. Absolutely. Okay, let's read from a graph. Let's read the function composition from a graph. It doesn't matter which one you choose. So we have in blue function f, and we have in purple function g. And let's say we want to determine f comma g of 1. F comma g of 1. What do I have to determine first? Always, I start with the inner. Very good. So which one? G of f comma g of 1. I have to determine g of 1. Are you with me? Okay, I don't think it's clear. Let me go back for a second. So let me write the problem here. Once we identify what we need to do, then we look at the book. So this is problem 92. We want to find f comma g of 1, which we know is f of g of 1. So we have to start from the inside. Ready? So we have to determine what one more time?
G of
G of 1. Excellent. So let's take a look. Can anyone identify G of 1? G is in purple. So G of 1 is, would you agree with -5? Good. So now I have to find f of -5. So can anyone give us f of -5? F of -5 is 3. So this, don't cross it out like that, I just want to make a point. So this was f of -5, and therefore f of -5 was 3. Any questions? Any questions? Inverse functions. When we started functions, chapter 2, we looked at 3 sets of bubbles. This was one set. This was another, something like that. And this was another. What do you think about this? What did we say about this one? Function or not? Furthermore, if I want to go back, it's still a function. So this is function and has a very important property. 1 to 1 meaning not just 1x to each y, to 1y, but also 1y to 1x, 1y to 1x, 1y to 1x. This is an extremely important property. We talked about it briefly. I said wait because it's coming up at the end of this chapter. Is this a function? No, this is not a function. We don't even talk about it now. And what about this? Is this a function? Is it one-to-one though? No, we don't need it for now. So you notice that only a function that is one-to-one will have an inverse that is also what? A function, right? Very good. That's our first note. Note, only one-to-one functions have inverse functions. They all have inverses, but they're not all functions. Only functions that are one-to-one have inverses that are functions as well. Functions. What if I have some graphs? How do I know whether a function is one-to-one by simply looking at its graph? So let's look at a few graphs. We know what this is. What type of function is it? Very good. Awesome. We know what this is. Perfect. We know what this is. Cubic. Very good. See how easy it is now to identify them because we went through that section 2.5 that initially we said, oh, what do I need this for, right? And now it really helps us. Okay. Now, do you think that this is one-to-one? By the horizontal line test, for each y, there is only one x. By the horizontal line test, for each y, there exists only one x. So this is indeed one-to-one. What about the quadratic function? For this y value, I read two x values. This is a function by the vertical line test. But is it one-to-one by the horizontal line test? No, not one-to-one. So we are applying now the horizontal line test, not the vertical. We established that they were functions, but now we want to know whether they are one-to-one functions. What about the absolute value? Is it absolute value a one-to-one function? No, by the horizontal line test, not one-to-one. What about x cubed? Is x cubed a one-to-one function? Yes, it is, because if I cross it out as many times as I want with horizontal lines, they will all cross the function in only one point. Question so far? I want to create an example with two functions that are inverses of each other. And I'll give you f, and you'll give me g. Yes, please.
You said
Jordan?
the graph on the left, right there, in the bottom left, you said that was 1, 2, correct?
Yes. It's one-to-one because I can cross it with as many horizontal lines as I want. All horizontal lines will cross the function in one point. If it crosses in two or more, it's not one-to-one. Crosses in two or more, not one-to-one. Better? Everyone? Okay, so I'm going to create a function by saying x minus 3. So what I'm going to do, I'm going to take $3 from one of you. You're giving me $3. Can you create the function that reverses that operation? Indeed. And now here's my question to you. What do you think that f comp g will equal to? And what do you think g comp f will equal to? Think for a moment. So in other words, I'm giving you $3, and 3 minutes later I'm saying, give it to me back. Give it back to me. Or another option is, I take $3 from you, and 2 minutes later I'll give it back to you. So what happened?